This is just a strategy. Okay, do you really need to follow it? Not really, but if you do follow it, that's better. When I'm doing problems, I like to do look at the diagrams and then fill in the informations. Right. Sometimes that makes for me, to visualize and then see better, right? How to write the functions and stuff. But everybody's different. So what we're gonna do is like basically, as I taught you way in the beginning of the semester, we will do 2-column approach. One column will be all the info and then manipulations that we need to write an actual functions, which is one variable functions, on another column. And after you write the function, that's where you're going to be continuing to find out the optimal solutions using the first derivative or second derivative test, whichever you want. Okay? And it's very important that you need to, write it all properly and then, give names. Right? So let's take a look at the first example.
This meeting is being recorded.
Find the dimensions of a rectangle with the area 1,000 meters square, whose perimeter is the smallest. So in this case, what is our objective? And what is the givens? That's what we need to know. Our objective is the perimeter is the smallest possible. Right? That's our objective. And we are looking for what? The dimensions. And then the given is the area. So we're going to do 2-column approach. Right? On the left column, what we're going to do is I'm going to put all the info, draw diagrams, inputs, label the diagrams. And on the right columns, it will be my objective. In this case, my objective is smallest perimeter. That's our objectives. So on this side, we know that this is a rectangle. So rectangle, that would be length and width. So the perimeter, this type of problem is like, I would say, elementary type, because the function can be written from a formula that we already know. So those kind of problems are always the easiest, in my opinion. So the perimeter of a rectangle, that will be 2 times the length plus 2 times the width. And what we need to do is we need to have a functions of one variable. I cannot have 2 variables. So therefore, what we're going to do is we're going to use the info that we have from this side. Here's length and width. The info that we know is area. That is what? 1,000. So I know that the area is length times the width. So depending on which variable you want to use, right, or write as a function, then you're going to try to manipulate right here. So I have 1,000 area and then length times width. And if you want, right, the function in terms of the width, you're going to solve for the length. So now what I can do is I can basically rewrite this formula into a function of width by replacing this length with 1,000 over W plus 2W. So which will give me, when I simplify a little bit, that will be P of W, that will be equal to 2,000 over W plus 2W. So we got the functions already. What we want is we want to find out the maximum or minimum of these functions, right? So what we need to do is, according to what we learned from the 3.5, we need to find out the critical number. So the critical number, that is when the P prime of W is equal to 0, right? So that will give us critical number. So taking the derivatives and set it equal to 0, so P prime of W, that will be equal to negative 2,000 over W squared plus 2. And we're going to set this equal to 0, so therefore P prime of W is negative 2000 over W squared plus 2. So, which by multiplying both sides by W squared, that will be 0, negative 2000 plus 2W squared. And when I solve for this, right, adding 2000 and then divided by 2, so that will give me 1000. And so therefore my W will be plus or minus square root of 1000. Okay? Since the length cannot be negative, so my W will be 10 square root of 10. So what we need to do is basically find out, right, the local maximum and local minimum. This basically tells me my critical numbers. So now it has become, you want to use the first derivative test or second derivative test, right, to find out your optimal solution. To justify this is optimal solution or not at this critical number. So what we do now is by testing it, which is here's 0, here's 10 square root of 10, right? And then it can be what? Keep on going. But there will be some restrictions right there, right? The reason why is because what? The length and the width, the area must be what? Only 1000. But what we don't care about is on this side that much. But you still need to remember what is your domain is. Okay. So in this case, when you test for the value of P prime of W, because that we are trying to use the first derivative test. So I can choose a number right here. So let's say if I pick 1, right, and plug it into the first derivative functions, that will give me a negative value. And if I pick a number bigger than 10 square root of 10, so 10 square root of 10, if you use a calculator, that's basically approximately 31. So if you choose a number like that's greater than 31, let's say choose 32, right? And when you plug it into this functions right here, so definitely that will be what? A positive value, because 2000, right, minus 2000 divided by 32 square, that is very, very small number. Yeah, I would say not that small. It's like smaller than 2 for sure. Right? So that would become what? A positive. So that basically tells me, you can see that it's going what? From negative to what? Positive. Right? So this will give us what? A minimum. Are we all following so far? This functions will give us a minimum at that point. Because that makes sense with what we want to find out, because we want to find out what? The smallest perimeter. Because when you plug it in, this 10 square root of 10 into the perimeter function, and that will give us what? The smallest perimeter that we can get on these functions. Okay? So now what we can do is we can talk about this by first derivative test. Right? This is the first derivative test. By first derivative test, P of W has minimum value at W equal to 10 square root of 10. Okay? Because that is the justifying part for sure that you need to tell me. Otherwise, you cannot really say that this is a minimum or maximum. So finally, what we can do is we can start answering the question, because the actual question is asking for what is the dimensions of a rectangle. So dimensions, we need to know what is our length and our width. So in this case, after justifying it, then I can say that my width will be 10 square root of 10. My length, that is basically what, 1,000 divided by the width, which is 1,000 divided by 10 square root of 10, and which that will give you also what, 10 square root of 10. And both of them is in terms of meter, so therefore this will be my final answer, the dimensions. Any questions before I move any further? So the step that we take is basically, one, you need to write down your functions in one variable. Two, we need to find out the critical numbers. And three, right, you need to justify that this critical number is a local maximum or minimum using the first derivative or the second derivative test. And then four will be, in computing what the question is asking for. So those are the steps that I want you to see and I need to see for your work.
The recording has stopped.
Questions? Difficulties?
I guess the only thing that would throw me off is that if the length and the width are equal, then it just becomes a square.
Square is a special rectangle.
Okay.
Right? If you go back and then look at the definition, a square is also a rectangle with all of the four sides are equal.
Okay.
Any other questions on this? So a lot of times these type of problem, I don't need to grade anymore after this step because the function is wrong, so therefore all the answer will be wrong anyway. Right? So I point that out way in the beginning of this class, which is in chapter 1. And that require a lot of practice, right, to get information out and then think about how to manipulate it, so on and so forth. Any other questions before we move any further from here?
Professor.
The fourth part, sorry.
Yes. Go ahead, one by one.
I just wanted to see the fourth part.
You can go ahead.
Number 4 part?
Yeah, I just wanted to see that part. Okay, thanks.
So it's basically because of the asking for what is the dimension, so I'm just putting this dimension. Sometimes the problem will ask you not the dimensions, what is the smallest, possible perimeter. Then you're going to be plugging back into what? This functions right here and then find out what the perimeter is. You don't need to find the dimensions. So read the question carefully, what the question's actually asking for the final answer. Okay, so next person, what's your question?
Sorry, Professor, I wasn't paying attention at the -1, the negative 2001.
Negative 2000?
Yeah.
Negative 2000, where did it go? Oh, right here. Yeah. Negative 2000. That's taking derivatives. Because when you look at right here, 2000 over W, right?
Yeah.
I write it as W over negative 1 power. So when you take derivative, this -1, bring it down and then subtract 1.
Okay, I see.
Right? Yeah. Any other questions? So making sure that you see the structure of this, process, right? I think if you did chapter 5 and then if you put in time and then dig through all those first derivative, second derivative tests using all of those, then I don't think you will have a problem, okay? Much of a problem on this step 2, step 3, those part, okay? A lot of times you will have difficulty in the beginning, which is writing the functions correctly. And notice that the way that I started, I never start with one variable functions right away. You can always start from what is your objective. Even sometimes you write it out, okay? And after that, you try to see, hey, can I use any formula? And then from that formula, you may have multivariable. And then from there on, you try to manipulate to get what? one variable functions. You need to, you can go step by step. You don't need to start looking at in the air and then spacing out and then try to figure out. Sometimes write it out will help you out. Any other questions? We good, right? Okay. I'm not going to go a lot of examples. Okay, I'm going to show you enough, and then we'll move on from there. So a rectangle storage container with an open top has a volume of 10 meter cubes. The length of the base is twice the width. The material of the base costs $10 per square meter, and the material on the side costs $6 per square meter. Find the cost of the material for the cheapest such container. So the cheapest, so we want what? Minimizing the cost. Okay. Okay with this so far? All right. So
This meeting is being recorded.
So it's giving you, telling you that there is a rectangular box, open top, with 10 centimeter volume, cube as a volume, and the length of its base is twice the width, and telling you that the base material costs $10 per square meter, and the sides material costs $6 per square meter. And what we want is what? The cheapest, the cost of the material for the cheapest. So our objective is cheapest cost. Okay. So looking at the picture, rectangular box. So I'm gonna draw a rectangular box. That's a rectangular box. And from here, what I know is the volume, right, is 10 meter cube. And it also tells you the length of the base is twice the width. So here's my length, here's my width, here's my height. And we know that the length is what? Twice the width. That's what we know so far. That's all. So from here, we know that the formula for the volume is length times width times the height. Okay. Now, what we want to do is we want to talk about what? The cheapest cost. The cost is based off on what? The area, right? The surface area. So what is our cost? It said that it will be $10 for what? The base area. So I know that it will be 10 times the base area is length times the width. Plus, and all the sides will be costing what? $6 only. So it will be what? $6 times all the sides, the area of the side. So the area of the front and the back is the same, which is going to be what? With the length, right? The area of the front and back will be what? This length and the height. That's what we need to multiply. So the area of the front and back is the same, so it will be 2 times length times the height. That will cost $6. And then plus the area of 2 sides. This area of 2 sides is basically using what? The width and then the height. So again, on the left and right, so there will be 2, so it will be 2 times the width times the height. So now I got the cost functions already, right? What is the cost going to look like? So
The recording has stopped.
any questions before I move any further from here? Are we all okay with this? So notice that I did not really start from like, one variable functions right away. I start from multivariable, and then from there on, we're going to try to like manipulate it to get one variable. Right?
Is the objective always to like make it one variable?
Because so far, we only know how to take derivative of one variable functions.
Mm-hmm.
Right? Because when we talk about the maximum minimum of what? A function. And then we only learned so far how to take derivative of one variable function.
So for now, it's just one.
Yeah. Because once you go into Cal 3, then you will be looking at, 3 dimensionals and then using the vectors. So there will be, you can basically talk about different derivatives, derivatives with 2 variable functions and so on and so forth. So, are we all okay with this so far?
Professor, can you go over the 6 times 2 times 3 times height plus 2 times 3 times height?
So you see that I put a 6 all the way outside because left, right, front, and back, those cost our $6 per square meter, right?
Okay.
So I need to find out what is the area of front and back.
Yeah.
So the area of the front is basically what? The length and then the height. You see that the blue line that I draw, right?
Mhm.
So I multiply the area of the front, which is what? Length times the height. And the back is the same area, so therefore what? Instead of you adding it, you multiply by 2.
Right.
Similarly for the 2 sides, right? Now look at the width right here, right? The sides, the width and the height, that will give me the area. So it will be the left and right, 2 of them, so it will be 2 times that.
Can you mute that person?
Yeah.
Okay.
Can you mute whoever that is? Thank you.
I think he's asking questions in it.
Oh.
Yeah. So okay with this? So now, how do we deal with this? There's too many variables for us, right? So we want to write it down into a cost functions with one variable. So let's move on. Any questions before I move any further from here? Okay. So
this meeting is being recorded.
Now what we want to do is we want to write a cost functions with only one variable. So that will really depend on what information do we know from the problems to manipulate it. So the problem basically tells us the volume of this box is 10 meter cubed. And we already know that the length is 2 times the width, and then with the width times the height. So by plugging in all the information that we have, now you can see that the height can be represented as what? The width also. And we already know that the length can be represented with the width. So now what's going to happen is my height will be what? You divide it by 2, that will become 5. And then you divide it by w squared. That will be representing the height. So now what I can do is I can rewrite this cost functions in terms of the width based off of the given information. So that will be 10 times 2 times the width times with the width plus 6 times, and I'm going to write it like this, 12 times because I factor out 2, okay? And the length is going to be what? 2 times the width, and the height is basically 5 over the width square, and then plus, and then the width times width 5 over the width square. Now what we need to do is what? Simplify this function, take derivatives, find the critical number, and justify that critical number is either maximum or minimum using the first derivative or second derivative test. If you want to use second derivative test, you need to take second derivatives. Right? So let's try to do this.
The recording has stopped.
So simplifying this, right? That will be what? 20w squared plus, when I simplify this part, And that will give me what? 10 on the top, and then W, and then 5W. So that will become what? 15W. We all following so far, right? So this will become 10W squared plus 12 times 15. So then I just said 180. Okay. Questions? Difficulties so far? Okay. So now, next step, what we want to do is we want to find out the critical number. Okay. So we want to find out the critical number. So C primes of W equal to 0. That will be what? Critical number. So taking derivatives of this cost function, that will give me 40W minus 180 over W squared. So when I set this equal to 0, right? So that will be 0 equal to 40W minus 180 over W squared. When I multiply both sides by W squared, that will give me 40W to the third power minus 180. And therefore, when I, solve for W, and first, I think you can basically divide everything by 20. So it'll be 2W to the third minus 9. So my W will be 9 over 2 cube root. Okay? And what we need to do is we need to test. Now we need to test the value of what? This. So 0, you cannot be negative number, right? And this will be cube root of 9 over 2. And once again, there is up bound also. We don't really need to, it's best that if you can find out what is the domain and range are, okay? But if not, that's fine, because what we are interested in is at this critical number right here. So what we're going to do is we're going to test the value of, right, W plus the cost function. So C primes of W. Okay. And cube root of 9 over 2. I don't know what that number is. Let me see. 9 divided by 2, and then cube root of it. That is approximately 1.65, so on and so forth. Right? So we can choose what? 1 right here. We can choose what? 2 right here to test it. Are you all okay with this? Okay, so let's continue.
This meeting is being recorded.
So after you simplify this cost functions, I got 20W squared plus 180 over W. And we want to find out the minimum and maximum, right, of this functions. Technically, we want to find out, is there any minimum or not, right? Because we want the cost, minimum cost. So what we do is we find out the critical number by taking derivatives, first derivative, and then set it equal to 0. So when I take the first derivatives and then set it equal to 0, and then solving for the width, that gives me cube root of 9 over 2. The cube root of 9 over 2 is approximately 1.65. So therefore, we can choose 1 in the first interval and 2 on the second interval to find the value of this first derivative function. So when I plug it in 1 into the first derivative functions, and that's clearly a negative value. And when I plug it in 2 into the first derivative functions, this will be 80. Then 4 goes into 180 is less than 80, so it will be positive number. So you can basically see that it's decreasing to increasing it, change it right here, that critical number, so it will be what? Minimum. Right? So now, what we can say is by first derivatives test, right? And we have found the minimum. So by first derivative test, right? The cost functions is minimum at when the width is cube root of 9 over 2. And the question is asking for find the cost of the material for the cheapest container. So we want the cost. So finally, to answer the questions, the cost is basically what? Substituting this cube root of 9 over 2 into the cost function, and which our cost function is 20 times with the width square and plus 180 over the width. So which is cube root of 9 over 2 and cube root of 9 over 2. So let's use the calculator and approximate this width.
The recording has stopped.
So help me out right there. Use the calculator. What do we get? Two decimal places because we are talking about money, so we can't stop at 2.
I buy 163.54.
163.54.
Yes.
Confirm?
Uh,
Someone confirm? What about the rest of us? Do we get it? Anybody else?
yeah, I got the same thing.
Okay, good. So then we can move on, right?
This meeting is being recorded.
So after punching to the calculator, we got approximately 163.54. That will be the minimum cost that we can produce with the given info, which is the volume is 10 meter cubes. Okay? That concludes this example.
The recording has stopped.
Do you want the answer in English?
Oh yeah, definitely. I forgot that, huh?
Yeah.
I mean, we did. I'm assuming that we did the word problem before, and then that's what I want. Okay. So let me just put that.
This meeting is being recorded.
So, like in the previous example, the important part is writing this functions correctly, right? And then using the, giving informations to manipulate and then put it into one variable. And the second step is basically to talk about the maximum and minimum. We're gonna have to find out the critical number. And then using the critical number, when we find out the critical number, we need to use the first derivative or second derivative test to justify this. At this critical number, we have a maximum or minimum. And then lastly, we'll be answering what the question is asking for. So in this case, it's the cost. And the previous example, I think I said it, but I didn't write it down. Remember all the, application problem, I want in sentence telling me your conclusions. So in this case, you can write it down like, the cheapest material, right? With the open top rectangular box with the volume of 10 meters, will be 163.50 full dollar. Right?
The recording has stopped.
Are we okay with this? Any questions? How are we feeling on this problem, this section so far? So if you're, if you feel like this is okay, that's normal because I'm guiding you through, right? And basically, what we need to do is we need to do ourselves to find out a lot of problems, like what's going on. So, ready for the next one? All right. So let's take a look at this one. This one is like very, plain one. It doesn't give you much. A lot of time when I'm doing a problem, I'm scared of, this kind of one sentence problem, then, a paragraph problem. Because a paragraph problem, I can analyze and get a lot of information out. One sentence, if you miss one, then you probably cannot solve the problem. So this is giving you find the point on the curve y equal to square root of x that is the closest to the point 3, 0. Okay. So this is an example that I'm going to show to you, how we're going to use like slightly different technique, okay, with what we learned before. Ready to continue?
Yes.
All right.
This meeting is being recorded.
So example 3 is find a point on the curve y equal to square root of x that is the closest to the point 3, 0. So here's my y equal to square root of x, and here's the point 3, 0. And we want to find out a point on the curve, which is going to be xy, and that is the closest to this point. So that basically means when we talk about the closest, that's basically mean the distance between these 2 points is the minimum. Right? So that's what I mean by what? The closest. Right? The distance is the shortest. So that basically tells us, what we need to do is we need to write a distance formula. So we want the minimum what? Distance. That's our objective. So the distance formula, that is basically what? D squared, right? It's basically the distance formula is D, the distance is equal to square root of x minus x sub 1 squared plus y minus y sub 1 squared. So this is the part that I'm talking about right here, okay? How do we write this distance in terms of one variable functions, okay? And basically this is what we can do, right? We know that there is 2 points, and I can basically use this 2 point to plug it into this formula. But before I even start this, take a look at if I write it down like d equal to square root of blah 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 blah. When I take the derivative, I need to use the chain rule right here with the square root. We already learned implicit differentiations already, so therefore I can make this problem a little bit neater. Okay, instead of writing into a functions notation, I can write it into equations notations. So I can basically square it on both sides, because taking derivatives for a simplified function or equation is the same, right? So x minus x sub 1 squared plus y minus y sub 1 squared. So I want to use these equations to find out our local minimum or local maximum. So now next question is, how do we rewrite it so that, right, it will be what on the right hand side will be only one variable. So that is basically plugging in the value first. Okay. Let me write the proper notations first so that you can see where I'm plugging in. Okay. So the formula is x2 minus x1, right? So now what is my x2 and x1? That's basically what these 2 points, the x coordinate from these 2 points. So I don't know one of them, so I can say that x minus 3 square plus, and then the y2 will be what? Y minus 0 square. So when I simplify this, that will become square is equal to x squared minus 6x plus 9 minus y plus y squared. So I have what? 2 variable right here. And this is where you need to really remember that the point that we are talking about, right? The x coordinate, y coordinates for these points is on this curve right here. So that tells us my y can be substituted for what? Square root of x, right? To get the value of y, it will be what? Evaluating the square root of x. So therefore, my d squared will be equal to x squared minus 6x plus 9 plus my y is basically what can be computed with square root of x squared.
The recording has stopped.
Any questions? Right here. Are we all okay with this?
This meeting is being recorded.
So what we're going to do now is we're going to try to simplify a little bit further on this, equation that we got, and then take the derivatives using implicit differentiation so that I can avoid that taking square roots, right? So that's what I'm talking about. Like, we're going to do a little bit different than the other problems in this. So I'm going to use an implicit differentiation to, take the derivative respect to x. Because now the distance is a function of x now. You can see that, right? If I take the square root on both sides. So once we got after we take the derivatives, we're going to find out the critical numbers. And then as usual, we're going to try to test using the first derivative test to find out the local maximum, local minimum.
The recording has stopped.
So taking the derivatives from here. So when I take the derivative respect to x, right, implicit differentiations, let me do this, simplify a little bit. Square root of x squared, that will be x, so it will be 5x plus 9. Right? And let me point this out, okay? I hate this when I see it when you guys write it down. And I will take out points from now on. What does that mean? You're differentiating at the end. No, it doesn't work that way, okay? So make sure you write it properly. Differentiation should be all the way in the front, the operator of this input functions right there. So be careful. Starting from now on, I will be very looking at detail on your writing. So when you take the derivatives, implicit differentiations, remember that the distance is a function of x, so we need to use a chain rule right here. So this will be 2d times with d prime, that is equal to 2x minus 5. And solving for d prime, that will give me 2x minus 5 over 2d. So what is d? Right? So we need to have derivatives functions in terms of x. So what is d? That is nothing but taking the square root on right here. So that will be square root of x squared minus 5x plus 9, substituting back. And that's what we got on the derivative functions. And what we want is the critical number, right? So the critical number is when the derivative functions is equal to 0. That gives us critical number. That will also tell us where in the x coordinates will help us to get the closest distance, right, on the curve. So that will be 0 equal to, right, 2x minus 5 over square root of x squared minus 5x plus 9. So which is 0 equal to 2x minus 5. And that will give us our x is equal to 5 over 2. And this will allow us to, you know, break down the interval and then find the value of the distant function, the first derivative functions. So I can plug it in 0 and I can plug it in, you gotta be careful right here. I forgot about that. The functions is not negative infinity to positive infinity because the function is y equal to square root of x, so the negative number does not apply. So it has to be from 0 to there. So making sure that you don't choose a negative value to test it. So I have, will test 1, I will test 3. Are we all okay with this?
Can I ask a question?
Yeah.
So if you look right next to the number line you're drawing, and d prime equals 2x minus 5 over 2d, where did the 2 go in the next one? Where you replace d with the square root?
I forgot. Thank you.
You're welcome.
That will not really affect s. That's a good thing, right? Because when you multiply both sides by this, denominator, that will be gone anyway. Otherwise, it will be a problematic. So next time, you tell, see, when I copy from one step to the next step, sometimes I leave out something. Make sure you let me know right away, okay? If I do that. Okay with this? Any other questions? Anybody? Okay.
This meeting is being recorded.
So after I simplify this, equations, that will be d squared equal to x squared minus 5x plus 9. And what I do next is take a derivative of this equations using implicit differentiations, right? Taking derivative with respect to x because d is a function of x. So therefore, when you take derivatives with respect to x for d squared, you need to use a chain rule, so that will become 2d times with d prime is equal to 2x minus 5. And then when you solve for d prime, that will give you 2x minus 5 over 2d. And we need to have derivative functions in terms of x, so therefore I need to substitute this d with the function, the expressions with x in terms of x. So all I have to do is what? Take square root on this step right here. That will give me d, right? D of x, right? Square root of x squared minus 5x plus 9. See that? That's what I got. So that's basically what I substituted right there, right here. Now, to find out the critical number, we set the derivative functions equal to 0 and then solve for x. So when I solve for x, that gives me 5 over 2, my critical number. So try to use this first derivative test. So put it on the real number line and then test it which interval will be increasing and decreasing, right? So we need to find out the value of the first derivatives. So when I plug in 1 into this, first derivative functions. The numerator is negative. The denominator is positive. Right? So therefore, this will be a negative value. And when I plug it in 3 into the functions, the numerator positive, the denominator is also positive, so it will be what? Positive. So as you can see, we have local minimum at 5/2. So that's basically what we want, because this is the distance is a function of x, and then we will get a minimum at x equal to 5/2, so which will give us what? A minimum distance. So now we can say that by first derivative test, the distance functions g of x is minimum at x equal to 5/2. So that is the justifying part. The critical number that we got is a minimum. And the question is asking for find the point on the curve. So therefore, what do we need to do? We need to find out the order pair. So I got the x coordinate already. On the curve, to get y coordinate, I basically substitute this 5/2 on the x. So it will be y will be square root of 5/2. So I have the order pair 5/2 comma square root of 5/2. So that is the closest point that we can get, right? The closest point to get from this 3, 0. So finally, you need to make a statement, final statements. This 5/2 comma square root of 5/2 on the curve is the closest point, right? The closest point to 3, 0. And like usual, let me point this out again. First step is trying to, get the functions in one variable, and then take the derivatives so that we can get the critical number. And then after we get the critical number, using the first derivative test or second derivative test to find out, to justify this is a local max or local minimum. And lastly, interpreting what the question wants. And this concludes this example.
The recording has stopped.
Questions, difficulties before we move on? You all good, right? Okay. So what we're gonna do is we're gonna take probably 10-minute breaks, right now. And then when we come back, we're gonna go over not all the example, not all of them. Maybe I will do 4 and 5, and then the last one I will just skip it. I think the last one is from your textbook. So textbook